Okay, so we're going to be going over the theory of matter today, and all matter and all creation responds to the changes in temperature in several ways. One of those ways is in regard to its physical state. Depending on the temperature, matter on Earth will usually be either solid, liquid, or gas.
To understand why matter changes state, it's necessary to first understand the temperature. To understand the temperature, it's necessary to understand the kinetic theory of matter. And the kinetic theory of matter says that all particles of matter are in constant motion, and that means that when the molecules are moving, the faster an object is, or of any size moves, the more kinetic energy it has.
There's a formula for kinetic energy that relates to kinetic energy to mass and velocity. It's EK equals 12 mv2.
The formula models the observations that kinetic energy goes up as the velocity increases. The kinetic energy of matter says that warming something, the faster molecules will go. Therefore, warmer molecules have more kinetic energy.
This is a key understanding for more which that it follows to regard for the states of matter.
So basically, the warmer it is, or the faster it is, the more kinetic energy it has.
Okay, and also temperature is another basic measurement that is related to many of the concepts that it will follow in the exploration of states of matter. Temperature is actually the average kinetic energy of the molecules in a sample.
Temperature scales that are commonly used include Fahrenheit, Celsius, and Kelvin. Most science relies on Celsius and Kelvin. To convert from Celsius to Kelvin, Kelvin equals Celsius plus 273 plus 0.15, and Celsius equals Kelvin minus 273.15.
And then to convert from Celsius to Fahrenheit, it's Celsius times 9/5 plus 32, and for Fahrenheit it's you divide it. Negative, is that whatever?
Celsius equals Fahrenheit minus 32 times 5 divided by 9. The states of matter depend on its temperature. When the average kinetic energy of the molecules is relatively low, then the matter is observed as a solid. Extremely low temperatures beyond what is normal can result in another state of matter called bose-einstein condensate, which will be discussed later. As the temperature goes up, it will go to a liquid. Ultimately, high temperatures of matter will be plasma.
All right, solids. Okay, so when in the solid state, matter has a definite shape and volume. Solids, if at any given time or temperature, will not change in the shape or volume. The size and shape of a block or of metal does not change unexpectedly.
This is because the molecules are bound to each other by force that are stronger than the average kinetic energy of individual molecules at a particular temperature. Though the molecules wiggle in place, they are not moving, which is significant energy to break the bounds that hold them in place.
So what does happen when the temperature goes up?
They move.
They move, and then when they move, what happens?
It becomes hotter and
It becomes hotter and takes up more space, right? We're going to use the document camera and we're going to demonstrate what happens when water heats up and the molecules start moving faster. So
like
I'm going to light the Bunsen burner. And we're going to add heat. So you can see the water level, right? So as the molecules heat up, ladies, what happens as the molecules heat up?
And then the molecules start moving.
So the molecules are going to move faster.
And has more kinetic energy.
They'll have more kinetic energy, and as they move faster, they're going to get farther apart. What do we say? The water level is going to rise, and if you're paying really close attention, you can already see that it has gone up a little bit already. It won't take very long. So in what has it been, 30 seconds or a minute, it's gone up almost to the red line. Can you see that? how hot is the flask? Put your hand on it. Is it hot?
Warm.
Like bath water?
Yeah.
So in just a small temperature change from like room temperature to bath water, it went up the tube fairly significantly, right?
All right. When liquids are in the liquid state, matter has a definite volume, but not a definite shape.
So let's show them what that means.
All right.
So using these two containers, you can change the shape of the liquid, right?
Yeah. So it's
Triangle.
the same amount of volume, but when you do it now, it can be a totally different shape. But it's still the same amount of water.
So volume of a liquid is definite, shape of a liquid is indefinite.
Yes. All right. Liquids at any given temperature change shape to fit the container in which they're kept, but they retain their volume. Pouring a liquid from one container to another changes its shape but not its volume, just like we demonstrated.
The reason that liquids change shape is because the kinetic energy of the molecules exceeds the force that holds them together in the solid. But those forces still are strong enough to keep them from simply scattering anywhere. The liquid sticks to itself, but not so strongly that it has a fixed shape. As the temperature goes up, the molecules in the liquid move more rapidly. The faster they move, the further they can get from the other molecules.
When in the gas state, matter has neither a definite volume or a definite shape, so it doesn't keep its shape, and it can also scatter around everywhere. At any given temperature, they can change their shape or volume to fill a container that they're kept.
So gases are going to fill the container. Someone's got some perfume, right? Who's got some perfume?
I do, I think. Maybe.
You have some? Can you get it quickly? So spray it on the desk by Ian. Lots of it. Ian, can you smell that?
I can smell it from here.
I can
smell
smell it.
I can
All right, so
smell
the gas is expanding because the molecules of the gas are not bound. They're going to fill the container. The container is the room.
Oh, I can smell that.
Okay, someone who said that?
But I can smell it.
Spags
Yeah,
can
I
smell
smell
it.
it now.
Ian smells it.
I smell it. I don't smell it.
Not yet.
Stuffy today.
Not yet. You got it.
Sorry, it smells really good.
Sick today.
All right. So the back row smells it now. So a gas is going to expand. It is not bound by a volume. It will expand until it fills the container. Okay. What flavor was that?
Juicy raspberry and sugar musk.
Yeah. Everyone can smell it. Maybe the people in the corner because of the way you smell it.
Yeah.
All right. So everybody. So that's gases. No definite shape. No definite volume. So at a constant temperature,
Solids have a definite shape and definite volume. Liquid has an indefinite shape but definite amount of volume, and gas has a indefinite shape and volume.
All right, bose-einstein condensate. A state of matter where molecule kinetic energy is nearly zero. When the bose-einstein kinetic state, all of the atoms of the substance behave as if they were a singular particle.
All right. When you get a temperature near absolute zero, something special happens. Atoms begin to clump. The whole process happens at temperatures within a few billionths of a degree, so you won't see this at home. But when temperature becomes that low, the atomic parts can't move at all. They lose almost all of their energy.
Since there's no more energy to transfer, all the atoms have exactly the same levels, like twins. The result of this clumping is the BEC. The group of rubidium atoms sits in the same place, creating a superatom. There are no longer thousands of separate atoms. They all take on the same qualities and, for our purposes, become one blob.
All right, now moving on to plasma. At extremely high temperatures or low temperatures, the kinetic energy of the molecules of the gas will be so high that the electrons become free.
Plasmas are created with conditions are such that the atoms shake off their electrons. The space is filled up with the atoms, nuclei, and atoms, but they are not bound to each other. From the framework of the kinetic theory of matter, plasmas exist when the kinetic energy exceeds the force that blinds the electrons to the atom. This happens at a very high temperature, very low pressures, or some combination of the two.
All right.